Thanks for watching. And the cool thing is that the maximum principle is not only true for Laplace's equation, but also for the heat equation. So here is our setting. Suppose you have a finite rod from 0 to L, where the temperature at position x and time t is given by u of xt. And the question is, where is the hottest temperature and the coldest temperature? So where is the hottest temperature and the coldest temperature? Temperature of a rod. Sure, u of xt. Of the rod. Because remember, for Laplace's equation, we said the hottest temperature and the coldest one is on the boundary. And there's something similar going on here. So without further ado, here's the maximum principle for heat. So suppose here U solves ut equals dUxx, then both the hottest and coldest temperatures are attained in one of three places. Then the max and the min of U is attained either initially, so at the very beginning, so think of taking a cake out of the oven right now where it's super hot. So initially, at t equals 0. Or at the left endpoint, so think putting a block of fire at the left, on the left endpoint. In other words, x equals 0, or at the right endpoint, so at x equals L, on the right. Endpoint, x equals L. So basically at the boundary, except it could also happen initially. Once again, once you put the cake out of the oven right away, it could be super, super hot. And so let me just illustrate this pictorially. So once again, what does this look like in terms of pictures? So here you have your rod from 0 to L. So that is your x in this case. And now let's include time. So as time increases, it goes vertically. Then the question is, where is the max and min of U on that region? Then once again, based on what I said, the max is either initially at t equals 0 or at the left endpoint at x equals 0, or at the right endpoint at x equals L. So to figure out both the hottest and the coldest temperature, you once again just have to look either initially, maybe here, or at the left or right endpoint. Either here or maybe here. So definitely not on the whole region. Right? This is the point x comma t. And just two more remarks. First of all, this is enough for us to prove uniqueness. So an application is the uniqueness of heat equations. And this, you have the pleasure of doing that on the homework. which is cool because now we know two ways of proving uniqueness. One is with energy methods, and one is now with the maximum principle. And also, not quite an application, but related, you may wonder, what about the strong maximum principle? So, is it still true that the max and min is only on the boundary and not inside? Unfortunately, it's not quite true, but there's something related that is correct. So, strong maximum principle. So, in other words, if the maximum is attained somewhere inside, so at some point x comma t inside, so it's max or min, is attained at some point xt inside the region, then while it is not true that u is constant everywhere, it is still true that u is constant up to that time t. So in this case, if the maximum is attained at this point, u is constant anywhere before that point. Constant. So let me write that down. Then u is constant up to t. And the reason is the future is unpredictable. So while you may know the heat up to the past, okay, you don't know what will happen afterwards. Heat can get extremely crazy, and there might be like bigger, hotter temperatures, for example, or colder temperatures. So that's why all we can say is that u is constant up to that time, which again is enough, in terms of applications and for our purposes. All right, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.